Having considered the perceptron algorithm and derived how we can get an optimal hyperplane to separate linearly separable classes, let us see the relationship between perceptron and the Bayes classifier. Okay. For this we will have to set up this 2 class problem. Consider a 2 class problem. Let P of I equals 1 comma 2 be the a priori probability, that is, you have some information as to what is the probability that a certain data point belongs to class 1 or class 2, you have the a priori probability. Let Cij be the cost of deciding class Ci when Cj is true. That means the data point is belonging to j, but you are treating it as I and there is a cost associated with that, and this holds for these pairs ij belonging to 1 and 2. That means I can take 1 and 2 and j can take 2 and 1 and 2, right. I can take 1 and 2 and j can take 1 and 2. Let P of x given Ci be the conditional probability density of a data point x in class Ci. So, with this setup we will formulate a risk function. So, the risk R is given by this quantity, it is C11 times P1, the integral of the conditional density given C1 over the space H1 where this is acting, right. I assume that it is class 1 and I decide the label as class 1 and the priori is P1. The priori is associated with the true class. The true class is 1 and what I am labeling is 1. So, this is correct. Similarly, if it is incorrect, so I assume that I start with class 1 which is correct and I incorrectly decide it to be class 2, the priori associated would be class 1 which is P1 and you integrate this over the space H2, observation space H2 of the conditional distribution of x given C1. That means C1 is correct and I assume it to be C2. There is a cost associated with the C21. Similarly, I land up with C12 times P2 integral over H1 the conditional density, I integrate over the conditional probability density Px given C2 dx, and this is incorrect. Similarly, here this is incorrect and C22 is correct. I assume that the true class is 2 and it is also labeled as 2, and the priori associated with it is 2, and I integrate this over the space H2 of the conditional distribution x given C2 dx, and all of these are vectors, so I need to put a bar. Now, any vector or any data point belongs to either the space H1 or the space H2. Okay, any data point belongs to either H1 or H2. Now, with this in mind, let us go one step further. The following quantities are obvious. One, the integral of p x given conditional distribution of data point x given C1 dx over this entire observation space is 1. Similarly, it holds for the conditional density of x given class C2, and this is also sort of obvious from practice. The cost associated in labeling the point as 1 given it was 1 should be less than the cost associated in labeling it as 2 given that it was 1, because there is a higher penalty that we incur by having a higher cost in doing this misclassification, right, and that is what it means from practice. So, this should be obvious. Now, with this we will simplify the risk associated with the 2 class problem. So, let us rewrite this risk again. R is C11. So, you should be now comfortable withCij's. That means it Cij is j is a true class label and I is what you are classifying the data point as. So, it is going to be C11 times P1 times integral over space H1 Px given C1 dx plus C22 P2 times the integral of Px given class 2 dx, and this observation space is H2, and you can say this is H minus H1. So, H1 corresponds to class 1. So, I just mentioned this. And this corresponds to class 2. Okay. Now, we do the rest. It is going to be C21 times P1 times this integral P of x given C1 dx, and this is over H minus H1 because it corresponds to H2 plus C12 times the priori P2 times the integral of this conditional density given class C2 over the space H1. Now, what we can do is we have to simplify this further. So, idea is keep C21 P1 plus C22 P2 fixed. So, this is somewhere we have to fix something, and the fix is that is, let us assume that we want to look at this cost for this of labeling this as class 2, right. It can go labeled from class 2 to 2, or it can be the true label can be 1, but I classify it as 2, and let us say this is the cost that I have. I have to fix this cost. Keeping this cost, I have to minimize the rest of the quantities. Now, let us simplify this. So, the risk R is C21 P1 plus C22 P2. We fix this. So, now if you observe this integral, we have C21 P1. If you observe this integral here, C21 P1, this is integral over the space H2. So, the pi that you have with H1 and what you have with H2, when the total integral is going to be 1. So, to get that pi in H2, it is 1 minus the pi in H1. So, what we have to do is we have to subtract that quantity. So, you have to remove this quantity, which is minus integral P1 C21, the density of x given C1 dx. Similarly, for C22, we will have to look at that quantity. So, if you go through this equation here, there is a pi which is P2 times C22, and this is integrated over H2. Since we want to express in terms of H1, we will subtract that quantity, which is P2 C22 the condition on C2 in the H1 space. I think this has to be written carefully, and we have the rest of the other quantities, which is what we have, which is integral P2 C12 Px given C2 dx over H1 plus integral C11 P1, the conditional density Px given C1 dx over the space H1, because all those in space H2 I want to convert it into H1. So, that is the reason why I kind of simplified it this way. So, now suppose C21 P1 plus C22 P2 is a fixed cost, right. We simplify R as C21 P1 plus C22 P2, plus we will simplify this integrals in this form, P2 times C12 minus C22 times P x given C2, integrate this over this region H1 minus integral P1 times C21 minus C11, the conditional density Px given C1 dx over the region H1. I want to integrate it over the space H1 and come up with a simplified metric, right. So, we want to minimize R. So, it is sort of obvious if you can, because there is some integral, all these are some quantities and there is one integral here and another integral here, and somehow if this total integral is made 0, then I am at the optimal risk, right. So, I want to get rid of this integral somehow. The integral which is over the space H1 must vanish for a threshold, and that happens if P1 times C21 minus C11 times P x given C1, if this is equal to P2 times C12 minus C22 times Px given C2, then that integral vanishes. But when we have to decide on this classification problem, if these two quantities are related by an inequality, if P11 times this is greater than this, then we decide as x belonging to class 1 and x belongs to class 2 otherwise. Let lambda of x be defined as this conditional likelihood ratio Px given C1 upon Px given C2, and let zeta be this quantity P2 times C12 minus C22 upon P1 times C21 minus C11. So, we have this statistic which is the likelihood ratio, and then we compare against this the threshold that we have. So, this is the threshold. So, this threshold is when the quantities are sort of we choose against this threshold and decide on these two classes. Okay. Now, if this lambda is greater than zeta, then it belongs to class 1 and it is otherwise, because this is how we set this decision rule. Now, if we sketch this as a schematic, we have a data point it goes to a likelihood ratio computation unit. You get lambda x compare it against zeta and then formulate your decision rule. As follows. Right, there is an advantage in doing this this operation, which is the likelihood operation in the log domain, and we will discuss this through an example. So, this is the basic idea behind a Bayes two class classification problem that minimizes a certain risk. Now, we will see this in the context of Gaussian distributions, and then we will carry out a simple exercise and try to link this example to the perceptron problem. That was our objective. So, for that we set up this Bayes classification problem. So, with this setup in mind, which is basically based on the likelihood ratio computation and the comparator to decide this two class problem, let us visit the Gaussian distribution case. So, we will start with an example. Let us consider a multivariate Gaussian distribution. So, the class C1 has the following quantities for its mean and the covariance. The mean is mu1, it is a vector, covariance is a matrix which is x minus mu1 times x minus mu1 transpose. Let us assume that for the purposes of simplification we assume that the covariance matrices are the same to be C. You can have C1 and C2, that is a more general version, but in our example let us make the covariance matrices to be the same. So, we take another class C2. So, the mean is different here, which is mu2, but the covariance is the same. And C in general is non-diagonal, and we assume it is non-singular. So, let us get the conditional densities right now. Px given C sub I is 1 upon 2 pi. So, we will assume it is a m variate, that means there are m variables in the coordinates of the random vector. So, it is 2 pi power m upon 2 determinant of the covariance matrix power half. So, this is the denominator, and if it was singular you would see that this determinant of C would be 0. So, therefore, that is the reason why we assumed that in this form. So, it is e power minus 1 half x minus mu I transposed covariance inverse x minus mu I, and this holds for I equals 1 and 2. So, let us make the following assumptions. Let us suppose P1 equals P2, it eases our task, but in general it need not be, and we will assume that misclassifications have the same cost. Which means C21 is C12 and C11 equals C22. Now, the log of lambda x, recall lambda x is our likelihood ratio, and we take the logarithm of lambda x, right. This is log, just write it again carefully, C1 against Px given C2, we take the log of this likelihood ratio. So, the 1 upon 2 pi power m by 2 determinant of the covariance matrix, square root of that quantity, right, that is constant and that kind of vanishes out, and we will take the log, the exponential, you can get rid of it. So, if you simplify this carefully, you are going to get minus 1 half x minus mu 1 transpose C inverse x minus mu 1 plus 1 half x minus mu 2 covariance inverse x minus mu 2. If you do the algebra carefully and you simplify this quantity, it is straightforward. I will write down the end result. This is going to be mu 1 minus mu 2 transpose covariance inverse x plus 1 half of mu 2 transpose covariance inverse mu 2 minus mu 1 transpose covariance inverse mu 1. Okay, so this is a straightforward algebra. You can simplify this. You will get it in this form. Now, I think what is important is to observe this quantity here and this quantity here. So, suppose we let, so I will write it here itself. Suppose I say W equals C inverse times mu 1 minus mu 2. Suppose I let W equals C inverse mu 1 minus mu 2, then this quantity here happens to be W transpose, right. W transpose is basically W mu 1 minus mu 2 transposed times C1 inverse transposed, and by virtue of this property I have C1 inverse transposed is C1, C inverse transposed is C inverse. Okay. So, I repeat again. So, if we define W equals C inverse mu 1 minus mu 2, then W transpose is mu 1 minus mu 2 transposed times C inverse transposed, and if C inverse transposed is C inverse, so then we have this quantity. We assume that C inverse transpose is C inverse. So, ponder why you have this symmetry in the covariance matrix, why these have to be symmetric. Okay. It should be straightforward. Now, this quantity here I call this as Bayes B. Now, you have an equation of the form y equals W transpose x plus Bayes, and this is a linear classifier. Now, what we really want to imply is the following. The Bayes classifier for Gaussian distributions, we assume that the variance, the covariance is the same, we assume that the covariance is the same and the means are different. So, in this case the Bayes classifier for Gaussian distributions is similar to the perceptron, because we can derive a hyperplane that can classify these points. But there are subtle differences. So, we have to pinpoint those subtle differences. So, we will comment upon that. Subtle differences between perceptron and Bayes classifier under the restriction that we had. Now, perceptron acts on the premise that patterns are linearly separable, right. So, this is one of the important premise. Perceptron assumes inherently that the patterns or data points are linearly separable, because this condition is required for the perceptron to work. But this is not the case in the case of Bayes classifier. You live with an error because you may have patterns that overlap and you may have to figure out a decision boundary based on that. So, I will write this in red. This is not the case in Bayes classifier. So, patterns can overlap. So, in the raw form, without the log transformation, patterns can overlap, but when you do the log transformation they may not overlap. Plus there could be also noise which can flip the other way around. The other subtle difference is, I will write this in red for all Bayes. Bayes classifier minimizes in some sense the probability of classification error. And in the case of perceptron it is not the case, because anyway you assume the classes are separable, so this does not imply. Point number 3, perceptron is non-parametric. This is very important. You do not assume anything about the distribution of the points, etc. And that is kind of the assumption throughout the neural networks course, that this is a non-parametric form, right. No assumptions on underlying distribution, because at times we may want to even estimate the distribution. There are ways in which we can estimate the distribution, whereas if you think about the Bayes, Bayes classifier is parametric. And last, perceptron update and convergence this is a sort of a qualifying statement, is simple and adaptive. Whereas Bayes is not. For example, if I have to figure out under different covariance matrices etc., then I may not get a nice form like what I had, but the perceptron can classify, but Bayes I will have to derive from first principles and really have to figure out what needs to be done. And the other important distinction is, what if, as I am getting data points, the weight and the bias have to be updated, right? If there is a change in the statistics and it is sort of a non-stationary environment, right? The statistics are not the same and I keep getting data points. In Bayes I cannot. It is difficult for me to model that scenario, whereas in the case of the perceptron I do not care, because I am just getting data points the way they are and I tend to classify them. So these are some of the subtle differences, and when you code up the algorithms and when you know the data points how they are, I think you can figure out which is best suited for your applications. Okay. So with this we will complete this module and we will talk about the backpropagation algorithm, which is basically an extension of this perceptron to multiple layers, and that is a multi-layer perceptron, and we will talk about that architecture, and that will be our journey for the next module.